My name is Sophia Flucker. Welcome to my presentation on total data centre environmental impact. So in recent years, data centres have improved their energy efficiency, but there's still a long way to go in terms of becoming truly sustainable. In this presentation, I'll give you an overview of the current landscape and discuss how data centres can become more sustainable beyond energy efficiency. Our company, Operational Intelligence, are data centre specialists, and we provide services to optimise risk and energy performance throughout the project lifecycle. Our team contributes to research and standards development in data centre sustainability. Let's start by looking at trends in the industry. We see ongoing densification. So as computing performance increases, one of the impacts is an increasing heat load per footprint and also higher temperatures emitted from the IT hardware. It's necessary that our cooling systems design adapts to cater for these changing requirements. This increasing densification is leading to a growth in liquid cooling, a trend which we see continuing. There are different types of liquid cooling. The slide showing a couple of options. On the top left, we have liquid on-chip cooling, where a fluid, usually water, is piped to and from the highest heat load components on the printed circuit boards, and we have a heat exchange via a cold plate. This is supplemented with air cooling for the other components. An alternative to this is immersion cooling, where the hardware is suspended in fluid, such as an oil, to remove the heat. These types of cooling potentially allow higher grade heat to be recovered, which makes heat reuse more viable. The link on the slide is for a London South Bank University project, where they are looking at a district heating and cooling network which incorporates data centre waste heat. Another trend is higher temperature operation. The diagram on the top left shows the ASHRAE recommended and A1 allowable ranges for air temperatures at the inlet of IT equipment. So this is a psychrometric chart which has been defined with Technical Committee 9.9, incorporating all the major hardware vendors. These ranges have expanded in recent years, and this is able to drive higher temperature operation, which allows reduced use of refrigeration and also more free cooling hours. As the range is expanded to permit lower humidity, this reduces our humidity requirements. So plant can be sized smaller and it doesn't need to operate so much. So this has potentially got a water saving also. We're seeing more data centres making use of free cooling. So the diagram on the right hand side is a particular design using direct fresh air free cooling. You'll see there's no raised floor and the air is delivered via a roof mounted air handling unit, which is supplying air to the facility below. This image shows the results of a study we've undertaken to analyse free cooling potential in different climates. The assumption is an optimised cooling design based on indirect airside free cooling, which uses adiabatic evaporative cooling rather than compressor-based cooling. The locations with a green dot can use this technology and supply air within the recommended range, up to 27 degrees C. Those with a blue dot would have temperatures within the allowable A1 range, which is up to 32 degrees. Locations with a tropical climate, shown in red, would require refrigeration in this kind of system. There are other benefits if you can support a design with zero refrigeration. So not only do you have reduced energy costs from not having to run compressors, reduced maintenance costs where you don't have that plant installed. Of course, there's also the added benefit of reduced capital investment. That's not only in the mechanical plant which you have designed out, but it's also in any electrical infrastructure which would be necessary to support that and to support its peak load requirements. Regulation is also a trend for data centres. On the next slide I listed some of those regulations which apply. Some of these schemes are not necessarily aimed at data centres, but data centres are affected due to their high energy consumption and emissions. There is an EN standards series for data centres. Although compliance is not mandatory, it provides a framework for design and operation. This includes elements focusing on energy efficiency and sustainability best practices, as well as metrics which measure power usage effectiveness and use of renewable energy. There are a range of voluntary initiatives which look at this area. As well as other environmental standards, there are additional metrics such as carbon usage effectiveness or water usage effectiveness. The European Commission recognises the requirement to improve data centres' environmental performance. Their GPP guidelines, Green Public Procurement, are aimed at helping public bodies procure in a more sustainable way and considered life cycle impacts when producing the criteria. Building energy assessment methodologies have also been applied to data centres, although these focus on the building itself and exclude the embodied impacts of both IT and mechanical and electrical infrastructure. The European Code of Conduct for Data Centre Energy Efficiency has been running since 2008. This supports data centre energy efficiency by sharing best practice guidelines, which are publicly available on the website. Owner-operators can sign up as participants by reporting on their energy consumption and their adoption of best practices. Other stakeholders can achieve endorser status by reporting on how they support data centres in reducing their energy consumption. Participation in the European Code of Conduct for Data Centres is a requirement in some government tenders, and it's also been adopted by organisations outside of Europe. Like other industries, data centres are subject to increased public scrutiny of their environmental performance. One example of this is Greenpeace's Clicking Green report, which in previous years has highlighted which of the big operators are using green energy or fossil fuels. PUE is a metric widely adopted in the industry to measure energy performance. So in this example, we're showing the PUE and the energy breakdown of a legacy facility. So the ratio of total energy being used to the IT energy being used is 2, which means that for every 1 kilowatt we're using for our IT equipment, we have another 1 kilowatt in the supporting mechanical and electrical infrastructure, so in power, distribution and cooling. For a new build energy efficient facility in Europe, we'd expect to see the PUE a lot lower than this. So making use of operating at higher temperatures and free cooling, we might expect a ratio of more like 1.2, which is a big improvement on some of the legacy facilities. Although PUE can be a useful tool to analyse energy opportunities, it can also be misused in marketing. So it's a value that varies with both ambient conditions and load. We need to be clear on which PUE and which assumptions we're talking about when we state a value. In this case, you can see that at 100% load, our PUE ratio, our ratio for the IT load with the total data centre load is approximately 1.5. But down at day 1, where we first start putting IT equipment in the data centre, the ratio is much worse. It's around 10. So if we're designing things and optimising them for operations, and we're able to reduce our constant M&E loads, so the mechanical and electrical overheads, we can see an improved performance at low load and throughout the data centre's facility lifespan. Data centre sustainability is about more than just energy efficiency, however. Servers are typically refreshed every 3 years, and the production and disposal of their components has a high environmental impact. Life cycle assessment is an approach which takes a holistic, cradle-to-grave view of a product or service. This means that the environmental impact of all phases of the life cycle are included, from the extraction of materials, manufacturing processes, transport, installation or construction, the use phase, maintenance, disposal, and end of life. Considering the manufacture of components or subcomponents, this process requires raw materials and energy. Byproducts of this are emissions. These emissions cause environmental impacts, which cause damage to air, land, and water. Their environmental impacts may be quantified by analysing how damaging this is to areas of protection, usually categorised as human health, ecosystem quality, resource depletion, and climate change. Putting this all together, for a product, the total life cycle impact comprises that of the emissions from its subcomponents, those from combining them into the product, transportation from its location of manufacture to the point of use, its operational impact during the use phase, predominantly energy consumption in this case, and then further embodied impacts associated with disposal at end of life. A system comprises many products, and a building comprises many systems. Usually, focus is only on the energy consumption during the use phase of a building. However, by taking a life cycle approach, the embodied impacts associated with the manufacture, transport, and disposal of all of its constituent parts are also considered. In this LCA of a data centre undertaken by my colleague Beth Whitehead, the facility studied was located in the UK and used free cooling. It was assumed to be fully populated with servers refreshed every 3 years, operating at 50% of their peak power at 30% utilisation. In this scenario, the operational impact was found to be 4 times that of the embodied impact. Scenario 2 considered the same facility, this time located in Sweden, with reduced IT energy consumption and increased numbers of servers. This gave very different results, with the operational impact now half of the embodied. Scenario 3 now considered the same assumptions as Scenario 2, but with the location of the facility in the UK. In this case, the operational and embodied impacts were equal. One way of measuring environmental impacts is by attributing points to different areas of protection, with 1,000 points equal to the impact of an average European in a year. This helps with the issue of comparing different impacts which are measured in different ways. This table summarises research findings on the embodied impact of IT equipment, facilities infrastructure, that is, power and cooling systems, and the building itself on the different areas of protection. In summary, the IT equipment's embodied impact is around twice as much as that of the facilities infrastructure, in part due to its high refresh rate. The impact of the building is relatively small, hundreds of times less than that of the IT equipment and facilities infrastructure combined. Remember that these 2 high areas of impact are rarely measured. We can summarise key data centre lifecycle impacts as pertaining to facilities infrastructure and IT equipment. The equipment impact of both is significant. Electronics has high impact, as do the large quantities of metal found in the installed infrastructure. There are opportunities to dematerialise through design by using zero refrigeration, for example. Energy use of IT equipment may be reduced through virtualization and increasing utilisation rates. Often there are opportunities to reduce energy consumption of cooling systems, which can be reflected in lower PUE values. The source energy is also important, particularly when this is being consumed on an industrial scale. It is relatively easy to put forward a business case for energy efficiency. Reducing consumption reduces operating costs. Dematerialisation can allow reduced capex, and buying renewable energy has an impact on brand value. My colleague Beth Whitehead is currently working on the Sadassi project to build a circular economy for the data centre industry. The aim of the project is to reduce environmental impact by reducing waste and material consumption and extending product life through equipment reuse and remanufacture. You may already have watched Beth's presentation on circularity in the data centre earlier this morning. Thank you for your attention. That brings my presentation to a close. Please let me know if you have any questions.